So it's now time to reap the fruits of our labor in the previous session, where we derived the Lagrange interpolation formula. Now we want to see how to apply the formula to obtain an interpolating polynomial that passes through the given points. And then once we have the polynomial, then use it to find the values of the polynomial and its derivative at some specified points. Now, so when you are given points or given this table, so the best thing to do is to number them. And by default, the first value given in the table here, which is, so this becomes our x0, this becomes our x1, this becomes our x2, this becomes our x3. If this x0 by default 0 becomes f0, this becomes f1, this becomes f2, this becomes f3. I remember when I write f0, I mean the value of the function at x0. When I write f3, I mean the value of the function at x3. So you should be aware of that given notation. So the main thing with this Lagrange interpolation, once you know how many points you have and the kind of polynomial you need, you have to write the formula, including the Lagrange functions, LIs. So solution. So P3 of x, or simply the function f of x that I use to carry out the interpolation for these given values in the table, will be given by L0 of x, value of f at x0, plus L1 of x times value of the function at x1, plus L2 of x, value of the function at x2, and then we are only going up to x3, so we'll have L3 of x multiplied by f3. So remember, I can write f0, or I can write f of x0, or I can write y0. I can write f1 or f of x1, or just write y1. So whichever I decide to pick, I will still be okay. Now, even before now, I go into the nitty-gritties of the question. Let me make some things clearer on the application of the Lagrange interpolation formula. You see, for this question, we are interested in finding a polynomial involving x. So P3 of x, or it may be f of x. So when you are writing your formula, you write it in general form. But assuming the question was interested in you obtaining the value of the polynomial, say, at just specific point, say P of 3. Assuming you have been asked to find the value of the function or the value of the polynomial at x equals to 3, you will rewrite the same thing, but instead of writing x, you write 3. So if they had asked for us to find P3 of 3, so I'll write P3 of 3 equals to L0 of 3 times F0, L1 of 3 times F1, L2 of 3 times F2, L3 of 3 times F3. And I just substitute directly and I get a value. But if they ask for function, then you write the formula in general term x. So that's one. And then number two, you replace in the values of the f values as given in the question. So here we'll have L0 of x times f0 is given as 0, plus L1 of x, f1 is given by -1, plus L2 of x. F2 is given by 0 plus L3 of x times F3 is given by 15. And we are lucky for this particular problem because some terms will give us 0 because F0 and F2 happens to be 0. So instead of us struggling with that, with those terms that already have 0, taking the Lagrange function times the Fi value, we simply now say that this is going to be 0, and then the other value at F2 is also 0. So this is also going to give us 0. So it turns out that P3 of x will be nothing but negative L1 of x plus 15 L3 of x. But please note that this is reducing to this formula of only 2 terms because of the nature of the values of the function given the question. Does not necessarily mean that in any case you assume F0 and F2 are 0. That is as per this question. So the key thing will be now to define L1 of x. And once you have defined L1 of x, define L3 of x. Now, remember the formula we wrote in 7 in the previous section was involving n plus 1 values. But in our case, we only have x0, x1, x2, and x3. So if you need a polynomial of degree 3, how many brackets do you need for Li, each of Li value in this given question? If we are dealing with a polynomial of degree 3, how many brackets do we need, both in the numerator and denominator? Remember, P3 means that the highest power of x after simplification should be 3. So that will mean how many brackets? Any trial, any attempt?
I think there'll be above
There will be?
brackets.
Remember in each bracket, the value of x is the starting one in the numerator. So there's an x minus something, there's an x minus something. But are you sure if you write 4, if you expand, what would be the highest power of x? The highest power of x, if you write 4 brackets, will be? Don't disappoint your high school math teacher. If I have 4 brackets and each bracket, the leading term is x, when you expand, what will be the highest power of x?
4.
It will be 4. But are we interested in the polynomial of degree 4? So we are interested in the polynomial of degree 3. So how many brackets do we need? 3. We need 3 so that when you open those 3, you will get x power 3 is the highest. So that's the first thing to note. So you need 3 brackets in the numerator, also in the denominator. Because remember, there's always symmetry in the way we write Li values. Now, if I want to define L1, then that means that each first term in the denominator will be having which subscript for x? 1. So you write x1 minus, x1 minus, x1 minus. Remember, we have to choose our xi values from this pool. These are the only 4 values we have. I remember in the definition of Li values, there is no bracket that has xi minus xi in the denominator. So since that in this case, we want to define L1, and that dictates that each first value in the bracket in the denominator must be x1, then these positions can never be filled by x1. Because if you put an x1 in these spaces here, you'll get a 0 in the denominator, which will make the fraction undefined. So once we put x1 here, then we eliminate possibility of x1 being being in any of these spaces here. So the remaining values will be x0. So we write x0 here, followed by x2, followed by x3. And in this formula, there is always some symmetry. When this is x0, this must also be x0. If this x1, if this x2, then this must be x2, and this must be x3. So let's replace in the numbers. So we'll have x minus, what is the value of x0 from the question? Negative 1. So minus 1 will give us plus 1, okay? And then what's the value of x2?
1.
1, so x minus 1. x3? x3 will be 2, so x minus 2. Divided by, what is x1? 0, so minus 1, and then 0 minus 1, then 0 minus 2. Then you simplify, we'll have x plus 1, x minus 1, x minus 2, minus is, so 0 plus 1 is 1, 0 minus 1 is minus 1, 0 minus 2 is minus 2. So what will be the final answer in the denominator? Positive 2. And then we know the first two brackets, x plus 1, x minus 1, is simply x squared minus 1. And then x minus 2, everything divided by 2. Please expand and tell me the simplified expression in the numerator. So x cubed minus, so I give me the final expression. So x cubed is the first term is true, followed by what is the coefficient of x power 2? Positive or negative? Negative. So negative 2x squared. And then what the coefficient of x term? Negative x, correct? And then the constant term? Plus 2, correct? So this is what we get as our L1. Then let's define L3. L3 of x will be given by, so how many brackets do I need in the numerator? 3, because we are still dealing with a polynomial of degree 3. So you expect to have 3 brackets, each of which has x as starting, opening gate power 3. So you have x and then minus, you leave us some space, x minus, and then x minus. Then if you have 3 brackets in the numerator, then by default, denominator must also have 3. And the first term, the first value in each bracket in the denominator, if I'm defining L3, becomes x3, correct? x3 minus, x3 minus, x3 minus. Remember, we are still making our choices from x0, x1, x2, and x3. And once you put x3 in the denominator at the starting value, there is no way these other positions can have x3. So what should I fill in the first space? x0, next space, x1 followed by x2. And remember to be consistent so that you don't confuse and miss or write some things which are not correct statements. With this being x0, this must also be x0. This must be x1. This must be x2. So we replace L3 of x will be given by x, our x0 in this case is so negative, negative plus, correct. x1 0, x2 1. So, and what is our value of x3? 2. So I'll have 2 plus 1, then 2 minus or 2 plus 0, then say, or simply 2 minus 0. So let's just be consistent with signs. This minus 2 minus 1. So we'll have x into x plus 1, x minus 1, and then 3 times 2 times 1. X plus 1 times x minus 1 is always x squared minus 1. So x squared minus 1 by x over 6. So this will be x power 3 minus x over 6. So this is the L3 of x. So therefore now the final value from our computation was P3 of x is given by negative L1 of x plus 15 L3 of x. So when you negate L1, we'll have negative a half into x cubed minus 2x squared minus x plus 2 plus 15 over 6 into x cubed minus x. I'm simply replacing the L1 and L2 into this formula. So open brackets and collect like terms and tell me what will be the coefficient of x3. open and collect like terms.
To x cubed.
Correct, 2x cubed. And what is the coefficient of x squared?
Positive x squared.
Positive x squared. And what is the coefficient of x? -2. So, and then constant term. -1, correct. So this is the required polynomial. So once you have the polynomial, you can always get the derivative of the polynomial, the derivative of the function, and then answer this other parts of the question. So P3 prime means the first derivative of this function of this polynomial. So P3 prime will be given by, if you differentiate this function, with respect to x. Six x squared, and then plus 6x squared plus 2x minus 2. And in fact, we can as well get the second derivative of the same function. What do we get? (12x plus 2). In fact, you can go ahead and get the third derivative, which will be 12. And then, so responding to the last bit of the question isn't a problem. So what would be the value of P3 derivative at x? So we have calculated that. The second derivative of that function we have also calculated. Can you now replace where there's x by 0.5 in the derivative of P3 and tell me the answer? If you replace negative 0.5, so the equation wanted us to calculate at P3 prime. So this, we are responding to this part at P3 prime. That will give us -6. I don't have that. Can you reconfirm? I'm not saying it's wrong, but just confirm. I have -1.5. So confirm that. That's what I have. And then can you get the value of P3 prime at -1? You get +2. Yeah, so that's what I have. So that's what you get for that given problem. So in a nutshell, to apply formula 7, you just need to know which kind of polynomial are you having, which values of x are you having, and then from the values of x you are having can help you to know the kind of polynomial that can be defined by such number of points. So sometimes you will be given points and they specify the degree of the polynomial to which you have to do the approximation. But sometimes they can leave the question open. If the question is open, what will guide you are the number of xi values. So you see, for instance, even if this they didn't specify that we have to get a polynomial of degree 3, would have as well gotten the same answer because we have x naught up to x3, which are 4 points, and 4 points can define a polynomial of degree 3. So we'll as well do the, we'll also get the same answer, even without specifying that we have to use a polynomial of degree 3. But if they specify a polynomial of degree 3 and you are given more values, then what you do is just to identify 4 values from that given table, and you fix x naught, x1, x2, x3, and then put the values into the formula and then work it out. Sometimes also, you may not be asked to find the actual polynomial, but you'll be asked to find the value of the function at a specified point, like what I was trying to explain here, when we have been asked to find the value of the polynomial at 3. So you will write the same formulas the way you are writing the Li values, but so where there's x, you'll be replacing it by that actual number. And so in your computation, at the end of the day, will result into a number, not things which involve the variable x. Then let's see how we apply the reverse process. So example 2. Find the value of x given f of x is 0.3887 and we have x, we have y equals to f of x. So when x is 21, f of x is 0.3706. When x is 23, this is 0.4068. When x is 25, this is 0.4433. So when they are asking for the value of the independent variable, that is application of the reverse or inverse process, or the inverse Lagrange process. If they are asking for f at a specified value, then you apply Lagrange formula directly the way it's given in 7. So by default, what name do we give to 21? X naught. So this is what you're going to give us, X naught. 23? X1. 25? X2. Then 0.3706? F naught. Then this next will be F1, and this will be F2. So even without being told what kind of polynomial can be used to interpolate these values, what comes into your mind? We'll be dealing with a polynomial of which degree? Degree 2, correct. So which means then, in this case, we are going to have, the question here, find x given f is 0.3887. Remember, you can call it f or you can call it y. So this is a problem on inverse interpolation. This is a problem on inverse interpolation. Since x is unknown, f is known. So by default, the formula will be x is given by L of f times x naught plus L, so this say L naught, L1 of f times x1 plus L2 of f times x2. Yeah, the same way you deal with direct Lagrange interpolation, in the same way we write the formula for the inverse interpolation, but the slight variation is that the x takes the role of f and f takes the role of x. So this will be the same as, okay, maybe before I write the next step, we can as well just replacing the values of x naught, x1, and x2. So I'll have 21 L naught of f plus x1 is 23, L1 of f plus x2 is 25. So if we know the L naught, L1, L2, we will have a final value. But also, the value of the function itself is given by 0.3887. So this is to say that x that we are invested in will be given by 21 L naught of 0.3887 plus 23 L1 of 0.3887 plus 25 L2 of 0.3887. So keep in mind that if I say L naught of f in this case, how many brackets do I need? Numerator and denominator. 2, correct. I need 2 brackets because we are going up to f2. So this will be f minus. So if this is L naught, then this will be f naught. This is f naught. And remember that we have to choose from f naught, f1, and f2. So my first space will be taken by f1, and then this will be f2. Then f2, this f1. Remember, there's always symmetry. So which implies that L naught of the value given will be given by L naught of 0.3887. So F is 0.3887 minus, what is F1 according to our table? Correct. And then 0.3887 minus F2. Uh, 4433, correct. Then divided by our F naught. Correct. So there's always symmetry here. And then 0.3706 minus 0.4433. And then you will use your calculator to get a number for this L naught. Give this space, I will solve and fill in that space. And then what will be L1 of F? We know that we require two brackets. So we'll have F minus, then this will be F1 minus, F1 minus. So the first step, the first space will be replaced by which F value? F naught, followed by F2. Because remember, you can't repeat F1 in the denominator. So which means then L1 at the specified point will be given by 0.3887 minus our F naught is given as 0.3706. What is our F2? Correct, 0.4433. Then F1 is given by 0.4068 minus 0.3706, 0.4068 minus 0.4433. You'll also compute this using your calculator and get the numerical value of L1. Then lastly, L2. I know you have mastered the game. What should be in the first bracket? F minus which value? F minus F naught, and then second F minus F1, correct. Then the first bracket in the denominator, F2 minus F naught, and then there'll be F2 minus F1. Yeah. So you replace in the values. So L2 at 0.3887. So 0.3887 minus 0.3706. That 887 minus F1 is 0.4068. F2 is 0.4433 minus 0.3706. 0.433 minus 0.3706. In a similar manner, you use your calculator to get yes, the last term. But this is, yeah, yes, yeah, there's a problem there, okay? So it should be 0.4068. Yeah, I told you that when you are dealing with engineers, you don't have to worry. Things will always be taken care of. So if you work out the values of L0, L1, and L2, and you replace into the formula here, 21 times the numerical value you get for L0, 23 times the numerical value you get for L1, 25 times the numerical value you get for L2, and you sum them, you'll get the value of X. So if you do the correct thing, you get something close to this. So X will be approximately 21.999. There may be some decimals there. So which is roughly 22. But confirm. So you get the values, the numerical value of L0, L1, L2, replace into the X equation, you will get something close to 22. So that is generally what we do. And when you're given more values in the table, then you can apply the same thing and extend the formula to as many points given as you can. So that's all about the Lagrange interpolation. And at your own free time, please read and make some writings or notes on the Newton divided difference formula, divided interpolation. So I'll be sharing some materials that can help you to do that, but since we have some previous classes, you can always check the link I shared. One key thing before we stop on the interpolation, note that for Lagrange interpolation and the Newton divided interpolation, the spacing need not to be uniform. So for this method, Newton divided interpolation and the Lagrange interpolation, the space between two consecutive values of X need not to be uniform. Like one value of X can be given at 0, another one can be given at 2, another one can be given at 10, another one can be given at, say, 19. So you'll have the value at 0, value at 2, value at 10, value at 19. So whether Newton divided method or Lagrange interpolation will help you to carry out interpolation for such cases. But the previous method on the Newton forward and Newton backward, they are only applicable when the spacing is uniform. But the Newton divided and Lagrange interpolation can do whichever way, whether the spacing is uniform or whether the spacing is non-uniform. So that should be clear from the start. So whenever you have a problem